Hi there, welcome to the video. Today we are going to talk about radioactivity. Our brain's response to the word radioactivity usually takes us into the realm of superheroes, or into some dark, reimagined, post-apocalyptic world after a nuclear fallout. There is rarely a middle ground. However, 120 years ago, the world had a completely different perception of radioactivity. From toothpaste and watch dials to water and butter, radioactivity was everywhere. So, what happened? How has this marvelous discovery, which was considered one of humankind's greatest achievements? Well, let's start with the basics. Everything we see around us is composed of elements with stable atoms. The subatomic component responsible for maintaining the stability of an atom is called the nucleus. Now, imagine that you're about to sneeze, but it hasn't quite come out yet. How does that feel? It might be strange to describe, but that's exactly what certain atoms experience all the time. The urge to expel the excess and regain stability. Inside an atom's nucleus, there are positively charged protons and neutral neutrons. These nucleons are held together by a glue called the strong nuclear force. This strong force cancels out the repulsive electrostatic force of like-charged protons and keeps the nucleus stable. The nuclear force has a short range of action and is dependent on the ratio of neutrons and protons present in a nucleus. However, we see that the balance between the forces starts to waver in a nucleus where the number of neutrons exceeds the number of protons. A nucleus that exceeds the threshold number of neutrons and protons that the strong nuclear force can hold together comfortably will become more unstable. More specifically, these scenarios give rise to unstable isotopes of elements. Just as your body, through a series of expansions and contractions, expels a substance with a sneeze, similarly, the unstable isotopes of elements fling out different particles or forms of energy to restore balance between the forces in their nucleus. During this process of attaining stability, they change into a new nucleus. It is exactly this property, namely turning into something new to attain stability, that we call radioactivity. The process by which it transforms is called radioactive decay. A nucleus can undergo nuclear or radioactive decay through the emission of alpha, beta, or gamma radiation, and sometimes a combination of all three. The alpha particles are relatively heavy. They can travel only a few centimeters in the air and can be easily stopped by a sheet of paper or plastic. Beta particles have higher energy and more penetrating power than alpha particles, but are less ionizing in nature. They can travel through the air, but can be stopped by a thin sheet of metal or even protective clothing. Finally, the most energetic and fatal form of radioactive decay is gamma rays. Yes, these are the type that supposedly turned Bruce Banner into the Hulk. This is a form of high-energy light emitted by a nucleus that is left at a higher energy state after an alpha and beta decay process, but must still return to a more stable, lower energy state. A nucleus can undergo all of these decays spontaneously and transform into a stable form within seconds, years, or even centuries. This rate of decay is decided by what we refer to as the half-life of the radioactive substance, which measures the time it takes for a given amount of the substance to become reduced by half as a consequence of decay. Measuring radiation. Radiation with enough energy to cause changes at the atomic level is called ionizing radiation. It can damage cells, so it's important to measure its potential health effects. But how? Units measuring ionizing radiation are commonly named after leading physicists in the field. The unit for radioactivity, for example, was initially named after Marie and Pierre Curie, pioneers of radiology. Scientists now use becquerel, Gray, and sievert as standard units to quantify radiation and estimate its impact on people. Let's take an example. Suppose Alex is standing close to a radiation source. The source emits radiation through decay or loss of energy of its unstable atoms. This radioactivity is measured in a unit called becquerel. Becquerel describes the number of atom decays over time. When Alex stands too close to a source of ionizing radiation, his body absorbs a dose of energy. This dose is measured in grays. Grays describe the energy Alex's body has absorbed divided by his weight, but grays don't give a full picture of the effects of radiation. Some types do more damage than others. Certain body tissues are more or less sensitive to ionizing radiation. To calculate potential health effects, we use a unit called sievert. Sieverts take into account the type of radiation, the tissues exposed, and how much energy they could have absorbed. The bigger the sievert, the higher the potential health risk for Alex. Since 1 sievert is a large quantity, radiation doses are usually expressed in fractions of sieverts. A person's exposure due to all natural sources of radiation, for example, is on average around 2.4 millisieverts a year. Here are 7 applications of radioactivity in daily life. Medical diagnosis. Radioactive isotopes are used in medical imaging, such as PET scans and nuclear medicine, to detect diseases and examine organs. Cancer treatment. Radiation therapy is used to kill cancer cells and shrink tumors in patients. Electricity generation. Nuclear power plants use radioactive materials such as uranium to produce heat and generate electricity. Food preservation. Radiation is used to kill bacteria and pests in food, helping food last longer and remain safe to eat. Smoke detectors. Some smoke detectors contain small amounts of radioactive material that detect smoke and trigger fire alarms. Industrial testing. Radiation is used to check cracks or defects in metal structures, pipelines, and buildings without damaging them. Carbon dating. Scientists use radioactive carbon to determine the age of fossils, rocks, and ancient artifacts. Thank you for watching.